Before I begin, I do want to give a little bit of thanks to some of my mathematical colleagues who directly or indirectly helped me prepare this talk. The first is my two PhD advisors, my former PhD advisors, whose names will come up in this talk, Ramin Taklu-Bigash and Laura DeMarco, who are both good friends of Maryam's, and who have communicated to me over the past couple of decades the experience of working with her and knowing her. The others are through their writings. Anton Zorich and Kurt McMullen and Alex Wright, among many others, have written very beautiful pieces on Maryam's work that perhaps are not as accessible as I hope that this lecture is, but inspired a lot of the directions that I decided to take when I was deciding what to tell you today. Okay? All right. So, and of course, thank you to Gresham College for hosting me and the London Mathematical Society as well. All right. So we are here today to discuss the work of one of mathematics' brightest modern stars, Maryam Mirzakhani. Maryam was an Iranian mathematician whose deep and creative mathematics received the highest accolades in our field, and a warm and enthusiastic woman whose life and work were cut short at just the age of 40 when she succumbed to breast cancer. What I would like to do today is to communicate to you some of Maryam's work, not just the mathematical content, though that is the main goal, but also a sense of why other mathematicians find her work so impressive and so compelling. Really, what I'd like to share with you all is the appreciation that I feel when I read Maryam's work, and to give you a sense of the excitement and the enthusiasm that she felt while she was working, so to pass on to you a little bit of her mathematical legacy as best I can. So Maryam's work considered the connection between two subfields of mathematics. The first is geometry, which is familiar to us basically from nursery, right? So geometry is the study of not just shapes, which we in mathematics more often call topology, but also notions of, say, size or distance or curvature that we can talk about on shapes. So even in nursery, we learn things like circle or triangle, these geometric objects, but we also learn some deeper notions in geometry like bigger and smaller, or we don't learn concave and convex in nursery, of course, but we learn that some things are round and some things are flat, right? So these are the geometric ideas that go into this field. And geometry, of course, has innumerable applications outside of mathematics, right? Physics, art, architecture, biology, and so on. But it also connects to many other subfields inside of mathematics, like number theory, the study of the whole numbers and prime numbers, or algebra. So the second subfield that Maryam's work involved is the field of dynamics, which is, roughly speaking, it's the study of a system which evolves according to some fixed rules, usually simple rules to describe. So what you should have in mind here, for example, is sort of the basic laws of motion describing the movement of planets in the solar system, right? This is a type of dynamical system described by somewhat simple rules. In this talk, our simple dynamical systems, well, there will be some very simple ones. In fact, we'll talk quite a bit about the dynamical system, which is determined by walking in a straight line. However, there will also be more complicated dynamical systems, like walk from a mathematical object you know to one that has similar mathematical properties. Okay? So Maryam's work focused on a family of mathematical objects known as Riemann surfaces, and she used dynamics to understand the surfaces themselves, as well as some more sort of metadata things, like understanding the collection of all such surfaces. So what we're going to do is we're going to take a tour of two of her most important contributions in that direction. But I actually want to start with a quick warm-up problem that she herself considered in her teenage years. Mostly, it's interesting in and of itself, of course, but I also want you to sort of see how, even though her career was cut somehow, what do I want to say? I want to say the warm-up problem will help you sort of understand how mathematics was treated in her work as an experimental and visual science, which is perhaps not how we think of mathematics. Okay? All right. So just a little bit of background, since I'll sort of discuss this problem that she thought about when she was 16. Maryam was born in Tehran in 1977, which was just before the Cultural Revolution, the beginning of the Cultural Revolution, which Islamicized the Iranian academia. This was fortunate in a sense that there was enough sort of educational stability by the time she left primary school that a lot of educational opportunities were available to her. She attended a very high quality and prestigious school for girls in Tehran. And by the 7th grade, it was clear that she had really a standout talent in mathematics. With the support of her school principal, she and her friend Roya Beheshti were the first women permitted to participate in the preparatory national mathematical competition and join the national team for what's called the International Math Olympiad. Okay? So the IMO, the International Mathematical Olympiad, is a competition held every year that is a competition in problem solving for pre-university students, and it really draws immense mathematical talent from around the world, countries around the world. And it is somehow famously difficult, despite drawing together some of the best trained and most talented mathematicians of their age. Well, you can see I have the points distribution from 0 to perfect score here is not looking so good at the high end for the 1995 IMO, for example. And so doing very well, so achieving a gold medal here at the IMO, or even better, obtaining a perfect score is something which is very rare. So Maryam attended the 1994 and the 1995 IMO as part of the Iranian national team. Here's a picture of the 95 team. You can tell which one she is. And scored a rather astonishing 2 gold medals, 1 point off of a perfect score in her first performance and a perfect score in her second. I mention this not because it's somehow the bar of mathematical caliber, but it gives you an indication of her level of engagement already at that age. And I think it's also worth noting that being a woman accomplished in mathematics and science in Iran at the time itself is not so unusual. While gender segregation was absolutely a feature of education there were quite a few opportunities still available to women working in science at the time. And as Maryam herself mentioned in an interview in 2008, she had to explain while she was living in the US quite a few times that she was in fact allowed to attend, well, she rather humbly says a university. In fact, it was the best university in Iran. All right. So I'd like to start with this warm-up example comes from a summer course that Maryam attended as a teenager. It was held at the university for gifted math students. And I will read this. You don't have to somehow squint if you're in the back row here. So this is a memory from Ramin, one of my 2 PhD advisors that I mentioned, in a very nice collection of memories in the notices of the American Mathematical Society in memory of Maryam's life and work. And what he mentions is that in this summer course, one of the topics that the professor had talked about was about decomposing graphs. I will mention what all these words mean. Decomposing graphs into disjoint unions of cycles, including this rather curious examples of tripartite graphs into unions of 5 cycles. And it was considered the first difficult case of a general problem. And he had asked the students to find examples where this was possible, this mathematical question could be answered, offering $1 for each new example. And by the time of the next lecture, Maryam had in fact not just found some examples, but found an infinite family of examples, along with ruling out infinite families of examples, so necessary and sufficient conditions for decomposability. I didn't choose to include it in the Zoom because I was sort of running out of work, but Ramin includes the joke that Maryam was obviously smart, but not smart enough to only dole out 1 example a day. All right, so I'd like to discuss this problem a little bit because it gives us a wonderful glimpse into the sense of exploration and persistence also that Maryam, indeed really any mathematician, must use to approach a new problem. So graphs, it was a question about graphs. So graphs, of course, are just visual tools that mathematicians use to model relationships, okay? So graphs are models for a huge array of relations and processes. So say network analysis and neural networks are certainly popular applications these days. There are applications in biology. I have here a network of protein-protein interactions you can see in the middle, as well as, say, computational neuroscience or social science and so on. But all of these fields are sort of using graphs to encompass a simple idea, which is that it's a visual mathematical encoding of the relationship between objects. So here is a hopefully friendly example and hopefully familiar example. You might have thought I should have chosen group B for my example, given the nature of the talk, but I am American and I didn't want to escalate any tension, so I chose group B. So the round robin stage, the group stage of the World Cup, is something that we can represent with a particular type of graph. So in this stage, the 32 teams are split into their 8 groups, 4 teams in each group. And inside any group, so here I've got Group B with Spain, Costa Rica, Germany, and Japan, we can represent the idea of playing a match by connecting the 2 teams by a line, right? An edge of the graph, okay? So this is our visual encoding of the relationship between objects, right? 2 teams are playing a match if a line connects them. So here I think of each team as somehow a point in my graph. These points are known as vertices in graph theory, and the lines between them are called edges. All right, so this property, so what is a round robin? A round robin is a type of competition where each team plays the other exactly 1 time, right? What that means for my graph is that each vertex is connected to the other by exactly 1 edge, okay? This property for a graph is what it means for a graph to be complete. Okay, a graph is complete if each pair of vertices is connected by exactly 1 edge. And in graph theory, so putting this particular graph aside for a moment, one of the ways that we study graphs and try to understand them is by breaking them into smaller pieces. Okay, this is totally a universal strategy in mathematics, right? We study whole numbers by breaking them into their factors, particularly their prime factors, right? We will see more examples of decomposition later, but in graph theory, what you might hope to do is to take your edge set and decompose it into some simpler collection of edge sets. All right, so decomposing a graph can help understand the structure and the properties of the graph. So here, for example, I have my group stage round robin, and each of the 8 groups actually, of course, we know, the graph should look exactly the same for each of the 8 groups, which is that each team plays the other. That is a complete graph on 4 vertices. And this decomposition can help us if, for example, we want to understand, I'm not sure how good my colors look from different angles of the room, but for example, if we want to go ahead and schedule the matches, right? And we need them subject to the restriction that no team plays 2 matches on the same day, right? So what I'm going to do in order to do that is I'm going to color the edges of my graph, where each color represents a day for the match. And so if I can color my graph in such a way that no vertex has 2 attached edges of the same color, then that means no team is playing 2 matches on the same day, right? And this decomposition, although it's sort of simple, especially since I started with a graphic that looks very simple, this decomposition allows me to promote this sort of very basic way of achieving that on this small graph to the larger graph that it is part of the decomposition for, okay? All right. So that's just a sort of basic example, but it gives us a hint of the utility, at least, of graph decomposition. Okay, so what was the actual question that Maryam considered? So the actual question, and in fact, I will just read the title of the resulting paper and then explain the words one by one, so was about decomposition of complete tripartite graphs into 5 cycles. Okay, we've already talked about what decomposition is. So what is a complete tripartite graph? Why do I say it that way? First of all, I've told you what complete means. Well, complete tripartite is slightly different. So this will take a little bit of explanation. A tripartite graph is one whose vertices, whose points, can be grouped into 3 groups. Okay? I have indicated that here by color, which I'm hoping these colors are sort of different enough from each angle that most everyone can see them. So the vertices are grouped into 3 separate groups, and the edges of the graph are completely determined by the vertex colors, which is to say that 2 vertices have an edge between them exactly when they are different colors. That's all, okay? So here I've got 3 groups of vertices. I'll start with the simplest one, blue, green, and red. And I don't have any loops, right? Nothing is attached to something of the same color. I just have 1 edge between every pair of vertices. Okay. This complete tripartite graph, I've got 2 blue vertices and 1 each of green and red. And so I have all the possible edges there except one connecting the 2 blue dots. okay? And so on. And if I've done my coloring correctly, you'll see that that's actually exactly what I've got. This is a table here of a lot of complete tripartite graphs with small numbers of vertices, okay? So that's what it means for a graph to be complete and tripartite. You can imagine this being useful, by the way, for modeling like a causal kind of relationship, if there's sort of A and then B and then C. These tripartite graphs can come in handy. All right, so what does it mean to be a 5-cycle then? Well, it's exactly somehow what it sounds like. If you start at a vertex and you travel 5 edges and you end up back where you started, you have formed a 5-cycle. So here's a 3-cycle, a 4-cycle, and a 5-cycle. And the question that was asked was, is it possible, or can you find examples, because I'm sure he already knew it was possible, of complete tripartite graphs which can be decomposed into 5 cycles? Okay, so let's stare at this table for a second. I mean, just to take a very naive try, I definitely cannot decompose this first one into a 5-cycle, right? I've only got 3 edges, after all. I need a 5-cycle, and I can't reuse an edge for a decomposition, okay? Generalizing that idea, it doesn't take you long or much experimenting at all to see, especially when you have this picture in front of you, that in fact we need the total number of edges to be divisible by 5 in order to have a 5-cycle decomposition. Okay? All right, so this is what's called, by the way, a necessary criterion mathematically, right? It's necessary for a graph to have edge number divisible by 5 if we have any hope of having a 5-cycle decomposition. So here are the 2 graphs in my table, which have edges, which if I count them, there's a total which is divisible by 5, okay? This graph has 5 edges. This graph has 15 edges, okay? You can either count by hand, or you can cook up a nice formula for the total number of edges based on how many vertices have each color, okay? All right, so the question is, here's at least 2 candidates for graphs which might have a 5-cycle decomposition. We know none of the rest can because they don't have the right number of edges. And so if you try and think about, is it possible to have 5-cycle decomposition, say, of this first graph? Okay, I know it doesn't look like a cycle, but maybe we could kind of like weave around and end up back where we started. If we start, say, at the green vertex and we travel around, it doesn't take long to see that we're going to run into trouble, right? So if we try and cook up a cycle, we're going to end up back at the green vertex eventually. And there's only 3 edges coming out of the green, so once we leave again, we're never allowed to return, right? And similarly, if we start at this red, we're going to have exactly the same problem. You can try starting at a blue, but actually, the red and green vertices are still going to obstruct what you're trying to do, because when a cycle comes into a vertex, it has to leave it again. Another way of saying that is that in order for a graph to be decomposed into 5 cycles, one of these complete tripartite graphs, each vertex has to have an even number of edges connected to it, right? There's another necessary criterion for you. This graph clearly fails because the green and the red have 3 edges connected. You can check that this graph succeeds. It does satisfy that criterion. We've got, I guess, 6 edges up here connected to the red vertex and 4 for each of the others. In fact, you can, if you are persistent and do enough experiments, cook up a 5-cycle decomposition of this graph. Okay? All right, so these kinds of experiments and deductions allowed Mirjam to make progress as a teenager overnight, or maybe 2 nights, I don't know how often the lecture met, to construct these these infinite families of examples for this decomposition. And so while this problem is in some ways elementary and very different from her post-university mathematical work, notice how different this is than the kind of mathematics you encounter in school, right? There's no algorithm that tells you what to do. It's not like when you learned how to differentiate and you learned a rule and then you applied it 100 different times, right? This is very little memorization. There's no technique. You already know how to solve the problem. There's persistence to draw some of these graphs in the first place, right? And to run these experiments to try and figure out what the obstructions, what the necessary and sufficient conditions might be. But there's also a sense of play and visualization and experimentation. And as a professional mathematician, Maryam had an extremely impressive technical ability that was, thanks to her tenacious work and immense talent. But she also had a very strong sense of the visual and the experimental. And this is really an amazing sort of, it's amazing that we can already see that in her work as a teenager. All right. Are you all warmed up? Because it's kind of, all right. So, Maryam's work after university was focused on Riemann surfaces. So Riemann surfaces are geometric objects. And what defines a Riemann surface is that if you look closely, if you put a Riemann surface under the microscope, then it really looks like the plane that we're all used to. In fact, there's something a little stronger that's true. So here I have a picture, by the way, of the Earth's surface, which is certainly a Riemann surface. So keep in mind I'm taking just the surface of the Earth, the sort of hollow Earth is a Riemann surface. If I zoom in, if I take a map which really zoomed, probably I want to do even better than this, zoom in on London or zoom in on this block, then it's something which really just looks like sort of the flat, normal Euclidean plane that we're used to working with. But Riemann surfaces have an additional feature, which is that there's a type of independence about whose map you're looking at. Okay? So do you know these tourist maps of London that are sort of like cartoons and the iconic things are really large and the streets don't match up to reality, anything like that? Something like that, where if I took my surface and I have these little patches that look like reality, but they don't quite match up like that, that's not a Riemann surface. Okay? A Riemann surface is one that not only has these little patches that look like reality, but they all join up in some kind of sensible way. Okay? All right. So Riemann surfaces, if all you're interested in is shape, right? So if you allow yourself to stretch things and pull things and skew things, if they don't have any boundaries, right? So I know that feels weird because we're used to thinking of Earth as a three-dimensional object, but again, we're only thinking about the surface of the Earth here. There's no boundary to really talk about. Then they really only come in certain types. They're essentially totally determined in terms of shape by how many handles they have, how many holes they have inside them. So here's one with no holes. Here's a donut or torus with one hole. Here's two holes, and so on. Okay? This number of holes is known as the genus of the surface. Holes or handles, however you prefer. So if you have, I don't know if anyone other than mathematicians has heard this joke, but if you've heard the joke about a topologist not knowing a coffee cup from a donut, I mean, I guess, yeah. This is what they mean. That's what both of those things are, right? If you are a topologist, if all you care about is shape, then all that matters is the number of handles that a Riemann surface has. Okay. However, we don't just care about shape. We care about geometry. And Riemann surfaces do come with notions of geometry. And when I say geometry, what I mean is a mathematical description of how to measure ideas of distance on the surface or length, angles or curvature, all of this kind of mathematical description in a way that is intrinsic to the surface. Okay, so here's where it gets really tricky. What does intrinsic to the surface mean? These are very nice pictures. However, they are wildly misleading when it comes to the geometry of the surface in all but one of the cases. Okay? So for this sphere, we see this sphere here, as I've got it in the picture, or as you think about it, sort of sitting in three-dimensional space. That picture is a very good representation of what the geometry that we can put on the sphere looks like. Okay? If I want to measure the length from one point on the sphere to another one, all I need is a good bit of string. Right? If I want to measure the angles between them, then I just need two strings. Right? The curvature of the sphere sort of curves outwards. That's real. That's an accurate description of the geometry of the sphere. Okay? However, that is not true for these other figures. So for anything of genus higher than 0, the picture is misleading when it comes to ideas like distance or curvature. Okay? Curvature in particular is the one I want to focus on. So the sphere has positive curvature, and it sort of bulges outwards, okay, instead of being flat or bulging inwards. One way that mathematicians characterize this that you might have encountered if you learn about these non-Euclidean geometries is that if you draw triangles, right, if you wrap rubber bands around your sphere and make a triangle out of them, the inside angles of the triangle will add up to more than 180 degrees. Okay, that's a characterization of having this kind of curvature, positive curvature. This torus, this donut, it looks like in some places it has positive curvature, in some places it has negative curvature, maybe flat somewhere in between. That is not true. This is not a good representation of the actual curvature of the torus. The torus is actually flat. If you draw lines, straight lines on the torus, and you measure angles inside of a triangle, they will add up to 180 just like it would if I drew it on this floor. Okay? We will understand a little bit more why that's true later in the talk. Okay? The hardest to understand, perhaps, is the case of genus 2, 3, 4, and so on. Okay? When our genus is at least 2, our surface turns out to be negatively curved. So the geometry we can put, the types of geometries we can put on the surface are all negatively curved. So people often describe this as sort of a saddle picture because that helps you sort of visualize what the geometry might look like. In particular, triangles have angles that add up to less than 180 in one of these negatively curved spaces. That's true everywhere on this surface of genus 2 or more. Okay? So the geometries we put on this surface, it's just this abstract description of how to measure distance, length, and so on, but the curvature, for example, has these features which are not well represented by these pictures. Okay, so you might reasonably ask, why did I not draw you better pictures? These pictures do an okay job of some things. So, for example, these pictures don't do a terrible job of representing distance. Okay, they do a very bad job of representing curvature. They don't do a terrible job of representing distance. And if all this makes your head hurt, I mean, sort of rest assured that that's also true for professional mathematicians. In fact, there's basically an entire subfield of geometry is about good models for these kinds of Riemann surfaces. However, it is in fact a theorem. It is known that you cannot come up with a nice, good model that actually represents the geometry and then put it into our Euclidean 3 space. And that's why I can't draw you better pictures here. Okay? All right. So each type of visualization has its strengths and weaknesses. We'll see a couple more throughout the course of the talk. Okay. So not only do Riemann surfaces admit geometries, these notions of distance or length, but Riemann surfaces in genus greater than 0 can admit lots of different geometries. In fact, infinitely many different geometries. So for example, here's a genus 2 surface, and maybe in some geometries the handle is very skinny, and in some geometries the handle is very fat. Okay? So there are different types of geometries that I can put on the same surface. And so how can we possibly understand them, right? We want to classify objects as mathematicians. How can we understand all these different geometries that we could possibly put on these surfaces? Well, the answer is the same as it was for understanding whole numbers and the same as it was for understanding graphs, which is the idea of decomposition, right? And if I told you, I'd like you to take this genus 2 surface and give me some easier to understand surfaces, what you might do is grab the nearest pair of scissors and cut this surface in half, right? Let's cut it into 2 genus 1 pieces. You would be exactly on the right track, okay? That is a very intelligent way to decompose my surface. However, you have just introduced a boundary to my surface, right? So all of a sudden I have this curve, which is a boundary for my surface. Please forgive my mess here. Remember, these things are hollow, okay? So we would sort of see the back of the interior of the other surface, which I am not capable of drawing. Okay, but so the point is, if we do this kind of decomposition, then we introduce a boundary to our Riemann surface. And so if we're going to use this technique to understand Riemann surfaces, really we need to understand Riemann surfaces where we allow these kinds of boundaries, okay? And so this is a lot of what Maryam's work focused on in the case of these hyperbolic geometries, so these surfaces of genus at least 2. So it turns out not to be a problem to allow us to consider boundary curves on these surfaces. In fact, all of these surfaces are built out of a particular subsurface known as a pair of pants. By the way, I often ask my students about like Americanisms and if they will embarrass me in front of crowds here. I asked my students about this, and because of course I know the difference in American English and British English for pants, and they told me first of all, that it would be fine. But second of all, that they had an anecdote of a Cambridge professor. I don't know if this is real. I don't know if even one of my colleagues who's watching this online or something, but of a Cambridge professor who was so unwilling to say pair of pants while he was teaching the geometry class that he called them T-shapes. I don't know if that's like T for trousers or T because it does not look like a T to me. I guess you could sort of topologically think of it as, anyways. But I found that a much more embarrassing idea than just saying pair of pants. So there you go. All right, so these surfaces are built out of pairs of pants. And there's, I did want to make the point that if you are sort of topologically inclined, you could imagine sort of inflating one of the legs of these and deflating another leg and see that what you actually have here is a sphere with 3 little discs missing. Okay, or 3 punctures, as we might call it. Okay? So it turns out that these are good choices for building blocks for the collection of all Riemann surfaces. Okay? They can always be decomposed into pairs of pants like this. But here's the thing. If we want this decomposition to remember, to respect the geometry that we put on the surface, we can't cut just anywhere. Okay? We need to make good choices of cuts. We need to make these sort of straight line choices of cuts so that everything sort of matches back up when we try and glue the surface back together from its decomposition. Okay? And these straight line cuts are what are known as geodesics. So an analog of straight lines that we're used to in our Euclidean world. All right. So what is a geodesic? In particular, closed geodesics are what we're going to be talking about mostly in this talk. So a geodesic is a walk that you take on the surface with no acceleration. Okay? No turns, no speeding up, no slowing down, and it's closed if you end up back where you started. Okay? So what do I mean by no acceleration? If I asked you to stand up and walk in a straight line, you would not walk off into space off the edge of the Earth, right? Despite the fact that the Earth is curved. You would walk along the surface of the Earth, right? It's a straight line with respect to the Earth's surface. And similarly, even in higher genus, there's a notion of walk in a straight line with respect to the surface. Okay? So even though it might not look like a straight line to us, from the surface's perspective, it's a straight line. So these are also sometimes called sort of length minimizing paths. That's true in a slightly tricky technical sense. If you sort of infinitely zoom. Okay, so geodesics on a sphere, for example, the closed geodesics on a sphere are the great circles on a sphere, so these lines of longitude, for example. On a torus, things get a bit more interesting. So there's this beautiful, sort of freely available movie of a ladybird following a geodesic on a torus. So this is a closed geodesic on a torus. So let me start the movie. So here we see our donut, our torus, and the ladybird will appear and choose a direction, and then walk along the geodesic, walk the straight line in that direction. And as you can see, if we were just sort of thinking in our Euclidean space, you might expect her to just sort of cut off the top of the donut, right? But that's not a straight line from the geometry's perspective. What she's doing is a straight line from the geometry's perspective. So here you see that closes up. So that's an example of a closed geodesic on the torus. Okay? So already you can see that from our perspective, these might be a little tricky to describe. Okay? All right. So understanding a surface is really somehow tightly bound because understanding a surface comes down so much to understanding these pair of pants decompositions, which have to be made along cuts from closed geodesics, is really tightly bound to understanding its closed geodesics. So Maryam's PhD work focused on precisely describing these things, essentially, from various sort of angles. So she completed her PhD at Harvard, by the way, in 2004, under the supervision of Kurt McMullen. And I sort of already highlighted this accomplishment as a teenager. She accomplished something which any professional mathematician would tell you is much even harder than 2 gold medals at the IMO and a perfect score, which is that her thesis was comprised of essentially 3 papers that went in the top 3 journals, international journals of mathematics. I will not tell you how that compares, for example, to my own thesis work. Very impressive indeed. But so what did Maryam discover about these geodesics? So I'm going to focus on, as you might see from sort of the words involved in these titles, I'm going to focus on one of these three topics because it's somehow the easiest to get a feel for, the friendliest to describe. So let me first start by analogy. I want to explain to you how one might go about counting an infinite set. Okay? And if you're familiar with this notion of sort of countability and things like that, that's not what I'm talking about. What I mean is counting a set in a way where we decompose it into sort of finite pieces. Okay? So here's a set of infinite things in mathematics, namely the set of prime numbers. Okay? There are infinitely many prime numbers. However, we can count prime numbers, that is, they become a finite set, if we impose a length bound. So if, for example, I'm only interested in the prime numbers with 100 digits or less, or fewer, at most 100 digits, then I can actually write down and count how many there are, right? So here I've hopefully written down correct counts for how many primes there are of 1, 2, 3, and 4 digits. In fact, it's well known now, in a statement known as the prime number theorem, exactly how we should expect the number of primes of length of, say, L digits to grow, okay? So if we impose a length bound, which unfortunately mathematicians don't love base 10, this is really in base E, so I'm being a little bit unfair, but I hope you'll forgive me for the sake of exposition. If you impose a length bound, like I only want my prime number to have at most so many digits, then as that so many increases, we have a good description of how many prime numbers there are, okay? And in fact, that growth is not quite exponential, okay? So it's almost exponential, but with a moderating factor. And perhaps the most interesting interpretation I should say here is that we know how many numbers there are, if we forget about being prime or not, we know how many numbers there are with, say, 100 digits or 1,000 digits. And one of the consequences of the understanding of this growth pattern is that prime numbers become rarer as numbers become longer. Okay? So this can be a really sort of useful heuristic describing how many elements of an infinite set have bounded length. Okay. So the amazing thing is that it's possible, in fact, even though every hyperbolic surface has infinitely many closed geodesics, they can still be counted if we impose a length bound, right? I told you the whole idea for these surfaces is that we had a notion of length, okay? And so we can certainly describe the length of a closed geodesic. And if we impose a length bound, then we can count them in the same way that we can count prime numbers of maximally, say, 1,000 digits or 100,000 digits, okay? And here's the sort of spectacular phenomenon that we see. There's a type of prime number theorem for geodesics of hyperbolic surfaces. So if we count closed geodesics on a hyperbolic surface, and we bound the length by some number L, then we can understand exactly how the number of closed geodesics on the curve grows. There's an additional assumption here that I'm not retracing a path over and over again. That's what primitive means, okay? And the growth is actually exactly the same as it is in the prime number theorem, okay? So the surprising thing here perhaps is not that these two growth matches. The really shocking thing, or at least what should be the really shocking thing, is that this growth rate didn't care what surface I started with. It didn't even care how many handles my surface has. It's totally independent of that information, okay? So this is a rather strong counting theorem for closed geodesics. Okay. What Maryam considered was a much more difficult, very easy to say out loud, question. So she was interested in counting not all closed geodesics, but rather simple closed geodesics. A geodesic is simple if it never crosses itself. Okay? So here is a simple geodesic on a genus 2 surface. Here is a non-simple geodesic on a genus 2 surface. Okay? And in a sense, of course, these simple geodesics are even more basic building blocks, right? And it turns out that they're much harder to find on hyperbolic surfaces. So let me explain a little bit why this is a tougher problem. So even though it's not a hyperbolic surface, I'm going to think about the torus because it's a good example for explaining this. So the torus, I mentioned before, has a flat geometry, and here's where it actually comes from. So we can visualize the torus as actually a square if we identify parallel edges of the square, so top and bottom, left and right, okay? I meant to have a piece of paper out to do this. If you have a piece of paper, you can imagine taking it and folding it up to identify the left and right sides. That would give you a cylinder. If you take your cylinder and wrap it around itself, so that's what I'm doing here, then you actually get this donut, a torus, okay? So this is where the torus geometry comes from. This is sometimes called like a video game geometry because you have this feature where if you somehow hit the left edge, then you emerge back from the right edge and so on, okay? All right. So the thing is that in this square model, a geodesic really is a straight line path, okay? So here's that simple geodesic from the last slide. If I translate it over to this square, all I'm doing is going in a straight line, keeping in mind that I have to sort of, when I hit the top, emerge from the bottom, and so on, until I hit another red dot, okay? Under the identification of the sides, all these red dots are the same point on the torus, okay? And so the description of simple geodesics on the torus is exactly the description of straight lines in this square model. So here's a better way to look at it, perhaps. If you don't want to think about sort of like this union of segments, then you can think about taking lots of copies of the square, just repeat it over and over and over again, and then this straight line, or this sort of pieces of straight line path truly becomes a straight line segment. Okay? And if you want to do this to think about all the possible geodesics on the torus, then you need to take infinitely many copies of the square. All right. So using this, we can translate our question about counting closed geodesics of the torus into counting integer points, right? So going back here, these were the vertices of my infinitely repeated squares. Integer points inside of a plane. And bounding the length just means that the length of the segment is bounded, so they live inside some disk in the plane. And so it's the same question as counting integer points, that is to say coordinates with integer x and integer y inside of the disk. Counting simple closed geodesics in the torus, however, is a more complicated question. So you can show that it actually comes down to counting what's called primitive. This is a different primitive, I'm afraid. Integer points in the disk. In this sense, well, sorry, it's actually the same primitive, but I'm going to give it a different definition. In this sense, primitive means that when I hit that, I take a segment like this, and I hit my integer point, that's the end of my segment, it's the first integer point that I ran into on my segment, okay? Sometimes people call this visible integer points, because if you were to look in a straight line, there's no other integer points blocking your way, okay? All right. So it turns out this second thing is a much harder problem. So counting integer points in a disk is basically the same as computing the area of the disk, right? You just associate, say, I have a point here, just associate it with the unit square that it's the upper right corner of, okay? That gives a pretty good approximation of counting integer points inside the disk. Counting primitive integer points inside the disk, this visibility thing, this primitivity that I mentioned, is really the same statement that the two integers defining the point have no common factors, okay? They're coprime. And the probability that two integers have no common factors is actually a relatively sophisticated piece of mathematics compared to computing the area of a disk. Okay? So that's to give you an idea. Of course, we're going to work in the hyperbolic world, but the torus really captures a lot of the difficulty that, in fact, new mathematics has to come in order to translate to the simple closed geodesic counting problem. Okay. All right. So now we're in a position to understand one of the significant results of Maryam's thesis work. So she provided the first precise counts of the number of simple closed geodesics on a hyperbolic surface, okay? So by precise, I mean that they were known to have this sort of polynomial growth, meaning that it's very rare for a geodesic which is closed on a surface, a primitive closed geodesic, to be simple, okay? But she gave precise values for these counting and how we should expect this function to grow, okay? All right. So notice in particular, by the way, this growth rate is polynomial. This growth rate is basically exponential. This is telling you that the probability a geodesic is simple is somehow decreasing as the length of the geodesic gets large. Okay. So more striking than even the results, I think, was the methodology, which was, rather than considering this counting problem on a single surface, which is what her result was about, like take a surface and here is the counting formula, she solved this problem by considering the same question across all possible geometries at once. Okay? So she did this by sorting the geodesics into groups, which are really somehow topological objects, which don't really see the geometry. And to give you an idea of what the sort of flavor of her method is, let's go back to counting integer points in the plane, right? One way I could have counted these things is, so I'm going to just use this sort of random choice of grouping, is to split these points into groups, and if I understand the groups very well and can count those, then I can count the total, right? So here I've split the integer points of the plane into groups according to parity. So if both coordinates are even, then the point is colored red. If they're both odd, they're colored blue. And if there's one of each, they're colored green. Okay? And the key feature here is that this coloring, the density of each collection, is independent of where in the plane we look. Okay? There's a homogeneity to this kind of coloring. And what that means is that if I take some transformation of the plane, which preserves the coloring of the points, then that transformation will not change the density of, say, the green points, okay, or the blue points or the red points. And so all I would need to count points inside of, say, the image of this disk, which is an ellipse under the particular transformation I chose, is to understand how the notion of length changed when I applied that transformation. Okay? All right, so this is a sort of toy model, although actually pretty reasonably descriptive, of the technique that Maryam used in this approach, okay? She implemented this idea by splitting geodesics into groups, so a finite collection of colors, if you like, known as mapping class orbits, and she showed that, in fact, they have this kind of homogeneity property that it doesn't matter so much where you look to understand the density of each group in the bigger space, okay? All right. So here is a fun application. So let's think about a genus 2 surface. When I say application, I mean as a mathematician. Here is some more fun maths for me to tell you. So here is a fun application to understand topological types, the shapes of geodesics that can occur on these different geometries. So geodesics can either cut my surface up or not, right? So in a genus 2 surface, there's sort of two types of geodesics, the ones that cut it into two genus 1 pieces, and the ones that don't cut it up, right? Like these yellow curves, if I were to cut along them, I would still just have one piece. The red curve, however, would split me into two pieces. So the yellow ones, which don't cut my surface into two pieces, are called non-separating, and the red one is called separating. It follows from Maryam's work that the probability that a geodesic, a simple closed geodesic like this, is separating is independent of the geometry that we put on the surface. Okay? In fact, you can write it down. And it turns out that the probability, so it's an asymptotic result, so you want to assume your geodesic is kind of long. But the probability that a long, simple closed geodesic is separating is very low. So in particular, it's 48 times more likely to be non-separating than separating. Okay? All right, which is not something people thought you should be able to get your hands on, just to put it in some context. All right, so the technical heart of Maryam's early work, this PhD work, was understanding this space of all possible geometries that you can put on a particular surface. So mathematicians call this a moduli space. So it's an abstract idea, but here's a very concrete example. A moduli space is basically a map. Okay? Each point in the space corresponds to a mathematical object instead of a place. So for example, the moduli space of all geometries that we can put on the torus looks like this pink region. Okay? And maybe over here we have a torus with pretty chubby handle, and up here we have a torus with a skinnier handle. Okay? Each point in this region corresponds to a different geometry, more or less, that we can put on the torus. Okay? We study these spaces because they help us understand the objects they contain. They're often interesting themselves, but also they help us understand what does it mean for two tori geometries to be like close to each other, right? So how to deform these objects. And that leads me to talking about the second piece of Maryam's work that I wanted to understand, or to communicate to you. So after finishing her PhD at Harvard, Maryam went to Princeton under a Clay Fellowship and then accepted a professorship at Stanford University. And in that time, she began a sort of long-standing and very celebrated collaboration with Alex Eskin. And what they were interested in studying was a different type of moduli space, which keeps track of objects known as translation surfaces. So these objects in mathematics arise, one of the ways they arise is about thinking about billiard dynamics. And so I want to describe a little bit of that to you now. And maybe here I should say that I should have mentioned in my thank yous, a thank you to Diana Davis, who made my earrings, which are pentagonal billiard dynamics, which we will see in a moment. Okay, so this study of translation surfaces, which I'll describe to you, I want to sort of motivate a little bit by talking about billiard dynamics. Okay, so you can get some sort of very beautiful mathematical objects right away by thinking about translation surfaces. This one is known as the necklace translation surface, which arrives from the pentagon. All right. So when you play billiards, if you have played billiards, or if you have studied, say, basic physics and thought about movement of light against a mirror, you know that when you shoot a ball against an edge of a billiard table, the angle at which it comes back out is a reflection of the angle at which it came in. Okay? And so here, I truly stole this from something called like Billiards Monthly or something like this. Here is an example shot on a billiards table where we have the white ball, it hits an edge, and then pocket. Okay? And these angles we can describe perfectly using this reflection principle. All right, so an easier way, so describing this path that the billiard takes is a little bit complicated as is. I need to understand these angles. An easier way would be, at least if you're one of us, to just reflect the billiards table instead of reflecting the path. Okay? So if I reflect the billiards table instead of the path, well, I get a slightly more complicated billiards table, that's for sure. However, I get a straight line instead of an angle made. And so here I've done it with the original shot. Okay? And why not just keep going, right? So I hit the top of the reflected table up here. Let's reflect again. And we now get a fully straight line path to our pocket. Okay? We could reflect again if we wanted, but that would be a little silly. That's just another copy of this surface downstairs. More intelligent would be to identify this top edge with this bottom edge, just like we did with the square when we were thinking about tori. Okay? Notice, by the way, that clearly whoever drew this illustration was not familiar with reflecting things. We do not get a straight line. All right. Okay, so this process is known as unfolding. Okay, so we unfolded the billiards table to get a new shape, and identifying parallel edges here, we obtain a surface. Okay? All right, so translation surfaces generalize this idea very broadly. So the amazing thing is that we get objects we recognize when we do this, right? So here, for example, I have an octagon and a little cartoon of how it glues up if I identify parallel edges, okay? So if I identify top and bottom, left and right, I've already done that with a square, right? I know that I get a torus, but of course I'm sort of missing the corners of my torus, and so there's a missing diamond here. Now, those sides are supposed to be glued according to being parallel as well. So if I glue one pair of sides, I get this sort of torus with an extra bit. And if I glue the final pair, then I end up with an extra handle on my torus, which is a genus 2 surface. Okay? So this probably makes your brain hurt if you have not seen it before. However, this cartoon does a reasonably good job of explaining the sort of folding and gluing. Okay. So we have seen these objects before. However, only in shape, because translation surfaces are these surfaces but not equipped with geometries in the sense that I mentioned before. Rather, what we're going to do is to define a sort of pseudo-geometry on the surface, which everywhere except for the corner points looks just like this flat geometry that came from the polygon. Okay? At the corner points, we have sort of bad behavior, not in the case of the torus, because the angles all add up to 360. But in the case of the octagon, these corner points all glue up to a single point, and that has angle, if you sort of run around it, has angle, which is 8 copies of 135, which I don't do math very well in my head, but that's definitely more than 360. All right. So these translation surfaces are surfaces which have some finite number of bad points and flat geometry everywhere else. Okay? And please believe me when I say that they arise in other parts of mathematics than billiard dynamics. All right. So what we're going to think about is, just like in the Riemann surfaces setting, we're going to think about the space of all possible translation surfaces. Okay? And the nice thing is that there's a very simple way to take a translation surface and get a new one. Anything that preserves lines and preserves the property of being parallel will take one translation surface and give you a new one. Okay? So any linear transformation, as we call them, applied to a polygon will give a new translation surface. And that new translation surface will share a lot of properties with the old one. For example, if we glue this thing up, yellow sides together, pink sides together, we still get something that looks like a torus, right? So the shape of the surface is the same. But this sort of almost geometry might be very different. So for example, in this square, the length of the longest diagonal, indeed the only diagonal length, is, say, if this is a unit square root 2, right? But if I apply a transformation to it, that length can get longer in one direction and longer in both directions, since I'm thinking about diagonals. Okay, but say a vertical line, for example, gets shorter. Okay? So not all properties are preserved by these kinds of changes, but some of them are. And so, again, what we get in the space of all possible translation surfaces is a way to group them. Okay? Where we say, okay, two of these surfaces are in the same group, they get the same color if they are related by one of these transformations. This kind of collection of all things that I've colored green, all things related to a given surface, is what's called an orbit of translation surfaces. Okay? And the study of this kind of object in dynamics is really ubiquitous, trying to understand orbits, right? Things that can be related to another by a simple motion. Is the sort of foundation of a lot of dynamical systems study, okay? And in general, describing orbits, or more precisely, if you're familiar with the mathematics, orbit closures, is a very hard problem, okay? So you might have heard of something called a strange attractor, okay? If you've ever encountered this kind of picture before. Often people sort of just generally speak of this in qualitative terms about, chaos and small changes leading to big changes and that kind of thing. A strange attractor in mathematics is a very precise object. It's an orbit of a certain dynamical system which has the property that if you sort of cut a cross-section, even though this is all a nice smooth, curve, looks totally straightforward, if you cut a cross-section, you actually get a very complicated fractal type set known as a Cantor set. Okay, so these orbits can be very complicated, and describing them is a very difficult pursuit. Just to give you another analogy which helps describe the complexity of this question, I don't know if this will appeal to anyone, but I found it sort of pleasing. It might seem hard at first instance to describe. If you play chess, you know how a knight moves, so I've got it up in the corner here if you don't play chess. It can move sort of 2 up and 1 over, or any rotation of that, or reflection. And if you want to try and understand the spaces a knight can reach moving that way, it's not that hard to show you or convince yourself that a knight can reach any space eventually. Figuring out how many moves it takes is maybe complicated. That's what this diagram is indicating. Fine, that's not so bad. However, what if I told you that I'm not just thinking about this, say, infinite chessboard, which has squares everywhere, but I'm taking any shape of any chessboard that I could possibly want to write down, and I want you to tell me exactly what all possible configurations of spaces that the knight could hit look like. How would you even attack such a problem, right? It's an immensely complicated problem, okay? All right. So nonetheless, in a monumental series of work comprising hundreds of pages, Eskin and Mirzakhani, and together with their collaborator, Amir Mohammadi, were able to answer this question for this space of translation surfaces. Okay, so they were able to describe what do these orbit closures actually look like. And in fact, what they found is that they are not complicated and fractal. They're actually described by simple polynomial equations. Okay? And this is a really ambitious piece of work that sort of draws on almost every field of mathematics that exists, or at least pure mathematics, and really a beautiful piece of math. All right. So here is a fun application of this work. It's known as the illumination problem. Okay? So you might have actually seen, if you live in this lovely city, a beautiful installation that was at the Tate Modern a couple of years ago. So this is, there were two, I think, installations of Kusama, which was this sort of infinite mirrored room filled with lights. So this is a good description of what the illumination problem is. So the illumination problem asks, if I have a room that is covered in mirrors on every wall, and I have a light source, is it possible that there is anywhere that stays dark? Okay, can we describe the set of points in the room which are lit? Because, of course, the light will reflect off the mirrors, right, and hit a lot of different points in the room. So in the billiard setting, you can think of this as taking a billiard ball and asking, is there anywhere on the billiard table that I could put a pocket that was never going to be able to be hit? Okay, now, here I've got a rectangular table. The answer is definitely no. There is no such point on this rectangular table because rectangles are convex, which is exactly the property I would need, which is that any 2 points in a rectangle can be connected by a line that is still in the rectangle. Okay? So this straight line shot can reach any point on this rectangle. I don't even need bounces off the sides. Okay? But for more general polygons, it turns out that this is not always the case. It's possible to configure or to construct a polygon with points that are not mutually illuminable, which is to say if I have a light source, say, at point A, or I hit this billiard ball at point A, it can never, no matter which direction I point it, hit this point B. Okay? So there are rooms or polygons with points that cannot be connected by straight line paths. And in fact, now that we've learned what unfolding is, this example is not so mysterious, okay? It is complicated, but not so mysterious. This example is an unfolding of a triangle, of this isosceles triangle. So it's not too hard to show. It takes some work, but it's not too hard to show that if you hit a billiard ball from this corner point A, it can never return to that corner point A, okay, no matter which direction you hit it. If you keep that in mind, and you hit a billiard ball, if you take any unfolding of this isosceles triangle with the feature that no interior vertex is anything except A, which is to say that any B and C vertex is always on the outside of this polygon, then in fact you will get something that can never go from any A point to any other A point. Okay? And as you can hopefully see in this picture, that's precisely how these 2 points were constructed. Okay? Because if we could get a straight line from here to here, then it would descend to a path from A to itself when we folded back up. Okay. So as a consequence of the work of Eshkin and Mirzakhani and Mohammadi, a ball on a rational polygonal billiard table like this actually has only finitely many inaccessible points. Okay? I can actually write down the list of points on this polygon that A cannot reach. Okay? Now, when I showed you the unfolding construction, that seems somehow eminently believable, right? Like I did some finite number of unfoldings. There's only finitely many A points. But please be advised, there are many, many non-unfolded. You can get translation surfaces not from unfolding polygons. There are more complicated translation surfaces. Okay? And the key feature is that this illuminability property is actually preserved by that notion of linear translation or transformation that I discussed, right? Describing a line here and then transforming this thing by a linear transformation, I still get a line in the new object. And so this is really a statement about an infinite collection of billiard tables, right? And you can rephrase it in terms of the moduli space, and that's where Eshkin, Mirzakhani, Mohammadi's work comes in. All right. It's worth noting that this is really false, by the way, if you allow general shapes. Okay? So if you don't require your shape to be a polygon with rational angles, then there are definitely possible not just infinitely many points, but entire sections of the room which can fail to be illuminated. So these examples give, so this is Penrose's room, so these examples give a red point, which is a light source, and the unilluminated is in gray. So here, almost all the room is unilluminated, in fact, even though the walls are fully mirrored. Okay? All right. So a second application of their work, which is somehow easy to phrase, is known as the blocking problem. And I'd actually like to play a quick video for you of a talk that Maryam gave in Princeton describing this blocking problem as an application of her work. This was described at a Princeton seminar in 2012.
You put 2 points. So the first point is maybe your child trying to escape, and this is your iPhone. She's trying to reach, and so lights starting from this point A, and then going point B, and you want to block point A from reaching B by finitely many points. So, assuming that your child goes only straight, it bounces off the edges. But in any case, it's like starting from A. Can I block B by putting finitely many points, which means any path, there are infinitely many, possibly infinitely many paths from A to B. Imagine that your billiard can be illuminated. So can I put finitely many points here so that any path between A and B, you put the dad here and the grandma here, maybe it's like the other people. So any way going this way, from A to B, this is not such a good picture, will go through one of these points.
So if you didn't hear the beginning of that, by the way, she, rather than taking a billiards description or a light source description, was describing if your child sees your iPhone in the room and only takes straight line paths, is it possible to block them from getting the iPhone by placing a finite number of family members in the way? All right. Maryam and her husband, John, welcomed their daughter, Anahita, about a year before that video was taken. And a year after that seminar, she was diagnosed with breast cancer. At the time, she successfully treated it into remission. And a year after that, she was awarded the Fields Medal, the highest honor in mathematics, and the prestigious Clay Award for her research. But the cancer recurred relatively quickly, and Maryam died on the 14th of July, 2017, at just 40 years old. Maryam's loss was deepest, of course, for her family and friends, but it was felt across the international scientific community, not just for her stunning career cut short, but for the loss of a woman whose life and work inspired us, with her ability to turn ambition into collegiality and collaboration instead of ego. She was willing to share her passion for mathematics with students and with colleagues alike. And she was brilliant and ambitious, but she was also kind and humble. And she was gone too soon. There are a number of wonderful tributes to Maryam's life. The International Women in Maths Day was the 12th of May, Maryam's birthday, a newly founded annual celebration. And there are many scholarships and prizes and schools in her name promoting the work of young and future mathematicians, particularly young women in mathematics. So I was lucky enough today to share some of Maryam's mathematics with you. This talk actually shares a part of a title with a wonderful documentary that focuses also on her life from the perspective of her friends and family, her previous teachers, and so I wanted to share with you the access to that documentary if you haven't seen it before. With that, I think I will thank you all for coming and maybe open up for questions.
Hello. Thank you very much for your talk. I appreciate how difficult it is to explain what must be incredibly complicated mathematics to mere mortals. Could you summarize, maybe this is an impossible question, roughly how your work does it relate at all to Maryam's work, or could you tell us a little bit about your work?
Yeah, I'm very happy to. This is not a person that I know. So my own work is in complex dynamics primarily, and so I have a lot of common features with Maryam's work in the sense that I study iteration of systems, so there's sort of what I call these orbits that Maryam studies, the objects that can be reached by a simple rule. I study this similar kind of thing, but the systems that I study are just defined by functions. And so you can apply, a function is just a rule that takes you from one number to another number, and you can apply it once, or you can apply it twice, or you can apply it 3 times. And what I work on considers what happens when you do that somehow infinitely often. And the type of work that I do, the common thread a little bit with what Maryam did and what I did is that both of these fields have a slightly unexpected connection to number theory. That there's, because The simplicity of the system means that you really only sort of need integers to describe what you're doing, if that's a sensible thing to say. And that means that you can make sense of it whether the numbers you put in are complex numbers, or real numbers, or whole numbers, or more exotic things like p-adic numbers, or numbers over some more complicated mathematical object like a finite field, or even more complicated than that. And so those common features mean that there are some arithmetic tools and arithmetic consequences of the type of dynamics that I do, and that's what I particularly focus on. And while that's not really what Maryam focused on in her own work, it is a consequence of her work that it is possible to do such things.
Thank you for your question. I'm going to pass over now to Dr. Kevin Houston from the London Mathematical Society.
Right, hello. Hopefully this is coming across. Is it? Yes? Yeah, that's good. Right, okay. I'm Kevin Houston. I'm the Education Secretary of the London Mathematical Society. And if you don't know what the London Math Society is, despite its name, it is a national organisation. It's involved in dispensing grants and helping people with their research, funding that sort of thing. We also have public lectures. If you want more information, then please go online, lms.ac.uk, and you'll find loads of stuff there, and maybe you'll even want to join. But anyway, I'd like to finish tonight by thanking you all for coming out tonight and enjoying such a great talk. I'd like to thank the people at Gresham for the wonderful organisation, and I'd like you to join me in thanking our speaker, Holly Krieger, for such a fantastic talk.